Hi, so my name is Marc Chiarini, as YY said, and I've been working for the past almost 2 years with Margot Seltzer at Harvard on applications of provenance. So for those of you who don't know about provenance, I'll go over a little bit, a short introduction to it, and then I'll jump into exactly what we're going to be addressing today. So, and for those who don't know, actually, this is Maxwell Dworkin, which is the computer science building named after the maiden names of Bill Gates and Steve Ballmer's mothers. So, my background is in IT primarily, and after a long and broad undergraduate education in computer science, I went to Virginia Tech for a little while, and then I went into industry. And I came back when one of my professors, my former professors, said, "Oh, you've been working in IT for a long time. I'm working on research in IT," which encompasses a broad swath of things. But since I've been thinking about provenance, I've been thinking about ways to help the IT community. And one of the use cases for provenance that I've come up with, and I think it's a good use case, is to use provenance for troubleshooting. Okay, so basically, the problem is that troubleshooting is hard on servers, on desktops. In general, it's a very hard problem, and it requires really good mental models. And a lot of the time, we as system administrators are putting out fires all over the site, and we don't have time to address the deeper problems, the infrastructural problems, for example, and get to the root cause of serious problems. We usually just put out symptoms. We put out fires and symptoms. So a lot of the time we're doing this. We're trying to develop our mental model, and all these fires are happening. And we can't get a grasp of the different components and dependencies in our system. So we often end up with a smoking ruin of a mental model about our systems. This is not conducive to actually doing your work at a deeper level. You know, you can continue to put out fires for 20 years, but actually getting to the root of the problem would really help improve your life and the life of all the people who use the system. So the solution really is not to hold it all in your head. Number one, because if you get hit by a bus, all that knowledge is gone. Right? If you never wrote anything down of significance anywhere about the systems and the experience that you've gained, it's gone. So what we want to do is we want to expose these hidden dependencies between components in our system, because these are often the things that give us the most trouble. We think we have a good mental model of something, and we start exploring it, but because of these hidden dependencies, which we don't know about, we can't get to the root cause of a problem. So ultimately, what I'm proposing that we do is build these models of component interaction that you can query. So we want to be able to ask the system, essentially, can you give me good advice as to where the problem might be occurring in the system? What components might be responsible? This could be, I'm talking about at the system level, the operating system level in this case, but this could be applied and extended to devices, routers on the internet, things like that. And how we do that is we collect and maintain the history of digital provenance, of digital objects, which we call provenance. Now, provenance we have a lot of in the physical world, right? We have the provenance of, for example, paintings, right, by Raphael, provenance for wine. And these are very important to people, right? Especially buyers and sellers, because they want to know who's touched it, where has it been, you know, who's modified it, right? And you can see some analogs and some parallels to system-level objects. So, and this was something that I wished was mine, but I'm going to have to give up on that dream. So, what are we talking about when we talk about system-level digital provenance? So there's been a lot of work recently on provenance, especially in databases And there's been a few use cases, and there's been some challenges, some workshops, and stuff like that. But Margot and I feel that we don't really have a burning use case yet. We don't have a really strong purveyor of using provenance for various applications. So the system-level digital provenance that I'm talking about is collected in the OS. So we record the history of these digital objects, processes, files, and pipes, for now at least, by intercepting system calls at the kernel level. Now, I should say that this work was already done by the time I got to Harvard in many ways. So I'm really just focusing on the use case of this, and I'm doing some work on extending this actual implementation so that it's not as fragile, moving it into the Zen hypervisor actually, which I'll talk a little bit about later. And of note is that all of this is time-stamped. So at least on an individual system, you have a total ordering of events of what occurred when. So if you open a file, you know exactly when that happened, according to the kernel. So what we record about 10 system calls. One of those is process creation, and of course it's analog process destruction. When we capture process creation, we capture all of this information, the environment variables, the command line, the executable file name, what time is executed, its parent process. So far, this has proven to be fairly useful, fairly robust. In other words, we don't have to necessarily add more information to it. We could, but this has been proven to be pretty useful at ferreting out the dependencies that we want to see. So the dependency graph that we're going to build with our provenance doesn't necessarily look like a graph that you expect. It is a directed acyclic graph, but when we talk about dependencies, or I should say potential dependencies, we point the arrow toward the ancestor of the dependent, right? So in this case, we're saying a file is opened or written by this process, right? And so this file is perhaps dependent on its existence and its content, dependent on this process for what it wrote or what actions it took. So we point the arrow in the direction of the dependence, right? So this is potentially dependent on that, okay? Now, dependency is kind of a squirrely word, right? It can mean a lot of different things in a lot of different contexts. And in the context that I want to talk about, in troubleshooting context, when I talk about a dependence, I mean that, for example, this process depends upon what's in this file or the existence of this file to actually behave properly. Now we get to another squirrely word, which is what is behavior. In the context for system administrators, I want behavior to mean the actions and the behavior that you've seen in your experience with applications and daemons and different system components that you've been working with. So Apache, if you see Apache always sends back files from the same directory when it's supposed to be sending back files from an entire directory tree, you know something is wrong. A lot of errors are much more subtle than that, right? That's a very in-your-face kind of error that something's strange and maybe something's misconfigured. So I'm going to leave this sort of as a little bit of a fuzzy idea. Behavior, of course, can be quantified, but normal behavior is a moving target, especially in open systems. Yeah.
Is the notion that the dependence is captured with this kind of single arrow between the process and the file? I'm imagining that real-life situations where there's an invariant that says the resources defined in one file will be referred to in another file. And in fact, it's not just that there's a dependence between the file and the process, but that the files have to be configured in a similar way.
Right. So We are not going to capture any content or really capture direct information flow between the processes. It's too expensive, and the process in the file. So we're trying to guess, in as lightweight as possible, what may be a dependency, a true dependency for the correct behavior of a program, or not. And so certainly, as we move on and explore more of what we can do with this provenance, we may be able to make correlations, right? There's usually no file that says, there's no meta file that says, well, Apache depends on these two files, and they have to be in sort of this kind of configuration in order to ever work correctly. Usually it's just the system administrator knows that you've got http.conf, and you've got some other, htaccess or whatever, and if these two things are configured correctly, your Apache will give you what you want. When things start breaking down, you want to know where to look. Where to look first is usually a gimme, right? But where to look second, third, fourth is the more difficult part. So you want to trace these sort of paths through this graph that we're going to be developing. So behavior. This process, let's say, potentially depends on the contents in this file. We also capture communication via pipe, which is relatively easy in Linux because it really just happens in the file system, right? Unix domain sockets, et cetera, IPC. We also capture memory mapped I/O. Well, we capture the system call mmap. We're not actually following the pages that are going back and forth, right? But just the fact that in some way this process is communicating with this file, transferring information, either reading or writing from memory mapped I/O. All right, so assume that we have some notion of provenance, that there's these objects, processes, pipes, files, and I hope to extend it to sockets and semaphores and other means of communication between processes. How do we organize it? So as I mentioned before, we can build these directed graphs, and they need to be acyclic because we have a time component here, right? We don't want to say that if a process reads a file and then writes to that same file, if it reads it at some later point, we don't want to say that the file is the ancestor, right, of the process, but the process is actually the ancestor of the file. We've got a chicken and egg type of problem. We keep going around in a circle. So we can't have any sort of temporal rifts, if you will. We want to be able to say that there's a pretty strict ordering. Something that comes before something else is perhaps causally linked, and the effect can't come before the cause. So we put these objects together, and the edges will then represent potential dependencies. And like I mentioned, we can't be sure that one object depends upon another because we're not actually tracking the content passed between the objects. We also don't know the semantics of the processes involved. We just know what's happening at the operating system level. So here is an example of a truncated provenance graph of a compile. Now you can imagine this as being part of, I've done the hard work for you, and I've pulled this compilation process out of a much, much larger provenance graph, right? And one example of this is, well, let me go over the overview real quick. So we've got our header files here, and we've got our source, and our compiler, and our assembler, and extra libraries that we're linking in, other object files, and finally the linker, and we generate our target, which is, this suite is called AMUtils, which is the auto-mounter utilities. And wire test happens to be something that tests being able to mount things over the network. So one thing I want to point out here is, yeah, this is all essential to this compilation process. And we kind of know this as developers or as administrators, right? Well, we have this interesting connection that I left in here, which is that these files were extracted from a tar archive, right? So our system is going to collect the fact that these didn't just appear out of nowhere, right? They came from somewhere, and this process ran and produced, actually wrote these files out to the file system, right? But this is not really important to our compilation process. It's important in the sense that we probably wouldn't have these files if we didn't untar it, but it's not really important to the compilation itself. So this is going to be an interesting task, which is to sort of discern where do you stop in the graph. You know, is tar interesting to me? You know, and then Marc installed Linux on this system interesting to me, right? If we let the graph, the paths go all the way back up through the graph when we're querying it, we're going to have some really, really long and big queries that give us a lot of uninteresting information. So here's a troubleshooting example. Okay, this is sort of the meat of what I'm getting to, and this is a very sort of stylized example, you could say, but it is a real one that I encountered. So many pieces of this is based on a true story. Let's put it that way. So let's say that I find my name resolution is having a problem. It's kind of cut off there a little bit, but so I know as an administrator that the resolver's a likely first candidate. As you know, the symptoms that are showing up is I can't get any name resolution. Well, maybe something's wrong with the resolver. And so I know that the resolver is usually configured by this file. Okay. Well, perhaps my provenance graph, collected that fact. It may have collected the fact that there were lots and lots of other inputs to a program linked with the resolver. But so traditionally, this file is edited manually, right, or by scripts sometimes, right? But modern-based Debian desktops, for example, they don't do that so much anymore. They have Network Manager configure this file. So I'm thinking to myself, okay, well, if Network Manager is configuring this file, what is it going based upon? What is it configuring based upon? I look in Network Manager's config file, and I find that there's no reference to name resolution at all, and not in the man page either. There's nothing about name resolution at all. Okay, well, Network Manager, I mean, he's supposed to be managing the network. Maybe he's not managing the host, itself. And the other key here was that in the resolve.conf file, there is a comment that says, don't touch this file. It's managed by Network Manager. Okay? So now I'm a little bit stumped. I'm like, okay, there's no mention of where's the communication happening? So I look and I see that amongst other inputs, including its configuration file, it's opened a socket endpoint, a Unix socket. So it's going to be doing inter-process communication of some kind, presumably. So it's communicating with some other component. I don't know exactly what it is yet. And remember that this graph is much, much bigger, right? I'm giving you the short story. Well, I trace it back and I see that, it's the dbus. So the dbus is a shared message bus that allows inter-process communication between you register services on the dbus, and then other clients can consume your services over this shared, it's essentially a multiplexer, right? There's lots of routes of messages going into the dbus and coming out of the dbus. And sometimes, and in fact frequently, the registration that happens for I'm offering this service happens long before its use, right? The service's use. Sometimes right at startup, right? The daemon communicates with the dbus and says, I'm going to offer this service, and then later on when things are running and processing, somebody communicates with the dbus and asks for that service. So normally this would be a really difficult thing to parse, and it still remains so even when you have provenance. My own sleuthing using list of open files, LSOF, and various other timestamps and things like that, registration names, led me to look through the dbus and find that the socket endpoint that was communicating through the dbus with the network manager was actually from this DH client. So the DH client is DHCP, right? And I thought, oh, okay, all right, now that makes sense. DHCP client is supposed to configure your host, right? It's dynamic host configuration protocol. So again, I'm trimming down everything, and I'm using my own experience to try to get to this point. Where is this guy residing? Well, now I know that this also has a configuration file. Hopefully it's not communicating with some other component through like the dbus again or something else, right? And I know that it's configured by dhclient.conf, and I go and I look at that file, and wow, you know, somehow this comment marker got put in there. So this basically is requesting. This should go away. Sorry, this thing over here. Anyway, it's requesting subnet mask, broadcast address, right? All of this is obtained through an ARP request, and basically we've cut out domain search and host name. So it's even unlikely that anything would, you know, any network type service would even start to run. It would just start complaining in the message logs that you don't even have a host name. I don't know where I'm supposed to be looking. I don't know anything. Okay. So but maybe this is just kind of a little bit of smoke and mirrors, right? I talked about magically finding the connection through the dbus, right? We give you this truncated graph. It's easy to parse, and especially when I'm explaining it to you, right? So what happens when your graph comprises thousands, tens of thousands, you know, millions of nodes, right? So something that looks maybe like this, which is small. This is not actual data from Provenance, but just to give you a general idea of the kinds of graphs that start to develop. This is real data from a real system. I experimented with these concepts of provenance before Provenance was sort of quote-unquote hot. So back in 2005, I started to question, you know, what if I just follow the paths that things take through the system? If I just focus on what files are opened by what programs. And there's a lot you can do statically, even before you get to this point, where you can say, you know, give me LDD on every single, you know, program in the system, and now I've got all of the libraries that they load, so I know all of those dependencies a priori, right? But there are also, like we've seen, inter-process communications and dynamic loading of libraries in certain cases. So this was a force-directed graph that actually got Margot's attention when I was at, I think it was NSDI, or OSDI. We can see like libc here is sort of the center of the universe in many ways, but also there's other ones. Etsy nsswitch.conf. A lot of programs are reading that via the resolver, or cupsd here is actually, this is not, these things are pointing into, so this is not really a provenance graph in the sense that I showed you that the dependency goes this way, but these things are not dependent on cupsd, but cupsd is dependent on these things, libaudit or some of these other connections. But this is a mess, right? I can't look at this and draw out useful information probably even in a programmatic way. And you can see that the larger graph is here. This becomes really, really, really messy. So what are we going to do? Okay, we have an absence of information in terms of semantics, but we do have some information about what's communicating with what. We do have a very elementary idea of where information might be flowing. So what we want ultimately is to rank the edges of the graph. We want to say, if this file is input by this process, what is the chance that it's actually a real dependency? The process needs this file to function correctly or in an expected way, right? So we want to be able to traverse the graph from one or more processes that are exhibiting unexpected behavior. These would be our symptoms, back to the root causes of that behavior. But again, for any process in the graph, we only know its inputs and outputs. We can't be sure 100% that this is a dependency. For some things we can. For some things we can. Some things, like I said, you know, libraries that it's linked with, that's a dependency. If that library is not there, or it's broken or wrong in some way, it's not going to run. So what can we do? Well, this is an extremely naive approach. And this is sort of speculative right now because I've yet to finish the prototype for this. So the kinds of provenance that we've gained in other areas like scientific workflows don't include sort of a really rich combination of different system daemons, for example, and configuration files communicating with each other. They tend to be very long chains of things that are repeated over and over again. For example, if you're doing a scientific workflow, you're going to get those kinds of configuration files that are read once at the beginning, and then you've got just whole bunches of data going through the pipeline. So I have this intuition that if a program reads from the same input, right, every invocation, at least once, then maybe there's probably a good likelihood that the program depends upon that input. Because it means every time I'm starting the program, it reads this file. Now, I can't know for sure, right? But I want to start with some kind of a ranking. So in my graph, I'm collecting the fact that this process is instantiated once in the past, 2 times, 3 times. And as I go along, I collect information about which files it reads every time it gets invoked. Right? So libraries are sort of a slam dunk. Right? I know that they're going to, in fact, I might not even have to, if I see that it's a library in sort of the prefab list of libraries, I might not even have to record that fact. I might just say that it's part of the characteristics of this program. Right? And when I say program, right, it comprises all the processes in the graph, right? So process objects, we're talking about nodes, that have loaded the same executable E, right? And perhaps we'll do, hashing on E to say that this is the exact same executable. And I'll talk about what happens if you have the same name or whatever, for example, but it's not the same executable. So the other intuition is that as time passes, that rank will become more refined. Okay? So, for example, maybe we start out just giving Apache a 1.0 rank on its connection to httpd.conf. Okay? Now, we know also a priori that this is not necessarily going to always be the case because I'm sorry, let me finish this slide. So in the case of Emacs loading etc.motd, we might have a very, very small ranking on that, a base ranking, because we see that there's tremendous number of files that are loaded by Emacs, and this is a very small portion of it. Not necessarily, a definite indicator that it's not dependent on this, and in many cases we know a priori that it's not, but we have to start somewhere. Yeah.
So, but actually I have a different opinion on this.
Please.
Basically, you're talking about troubleshooting, right? Failure often occurs because of some rare cases happens. So if you look at that particular bug execution, it's usually something different from the majority of the normal cases. So probably you should rank the things that only happens with this execution, but not in the others, higher than.
Well, there are, so there's some approaches we'll talk about in basically sort of refining your ranks and talking about other evidence in the graph that will point you toward whether you're talking about something that's a real dependency or it's not. Now, I take this, I take that suggestion very seriously. That often it's something that you're definitely not expecting as an input to the program, for example. There's only so much you can do without knowing what the program actually does, right? And so you may turn this on its head and look for the sort of needle in the haystack, which is nominally what we're doing, looking for, oh, it always loads this, it always loads these files. That's no problem. We know about those. But it loaded this file, at this time, and then immediately after it broke. So why, right? if that's the only evidence that we have, right, this ranking system, right, the base rank will fall down, right, because we'll say, oh, well, it's a low probability that it depends on this particular file. It was only read once or twice, you know, an invocation or something. But it's also related to when files were changed and how many actions, for example, was that file involved in, right, in the past. So we're always looking for correlations, if you will, between how often something is looked at and the popularity, per se, of an object. And those things will be perhaps less interesting. And I'll cover that a little bit. If I haven't answered you directly, I can take it offline. And so the caveats of this are that a lot of programs, you know, can be changed by command line options, right, or shell redirection. And this may very well skew our ratio, right? So you can imagine Apache for the past 6 months has been loading http.conf, and then all of a sudden a new administrator comes in and says, oh, we need to have all of our configuration files in, you know, this directory for Apache or whatever. And so he changes the directory that it loads from. Now you start gaining information that Apache's depending nominally upon another configuration file, a different configuration file. So now you start getting, you know, a 50% ratio on your base rank that basically half the time it loads this and half the time it loads that. Now you can trim that down and say, just tell me how many times it's loaded it in the past, you know, month or whatever. And if the alternate configuration directory has been accessed more, you'll get more evidence that that's the file, right? So, but since we record the environment and the arguments, we can actually treat these as different programs. So for every single program that you run with a different option, right, which we can quantify, we'll treat it as a different program and say it has a different rank. Again, probably a relatively naive solution, but I think it'll work pretty well, only based on my knowledge as a system administrator. And then in a similar fashion, we handle new versions of executables as basically new programs, right? Because you don't know what changed inside that program. Yeah. Well, it doesn't, you know, explode as quickly as you think. And you will be captured, you know, when we record provenance, our general ideal is to just hold on to that provenance for a long time. But eventually, you know, you can do an assessment and say, all of this provenance is now pretty much null and void because we've replaced all of these executables or programs or libraries or files or whatever characteristic you're looking at. Yeah, I mean, the provenance is still there in case you need to query it and go back and, you know, find out what happened. How did you get a virus 6 months ago and now it's just showing up, right? You might want to still look at the provenance. But my idea is that this is continuously running online in some way, and the you know, the configuration of it about what to elide and what to keep in the graph, for example, will have to be explored basically. So I want to talk a little bit about tweaking the ranks. So we've got this base rank, and actually I imagine this as not like, you know, you get a base rank and then you add or you subtract from that rank, but you have some kind of an equation that will, a multidimensional ranking essentially, right? So we'll take into account a bunch of these tweaks that I'm going to talk about. So we know that a lot of first-order dependencies are already, we know that they exist, right? So we know that SSH will almost exclusively never run if you don't have libcrypto shared object, right? It's either linked in dynamically, statically. It doesn't really matter. We know because we know that the functions in this file are necessary for that. So we do have a little bit of semantic knowledge about that, right? Again, we're bringing our system administration experience and other experience to the table. This may not be a completely accurate ranking, but it's a good start, right? Perhaps edges to files residing in well-known configuration directories should have their rank increased in some way, right? So, most files on a Linux system that exist in etc are for the purposes of configuration. So maybe we say, if we see that pam.conf exists in etc, we're going to bump up its rating by some amount, which remains to be seen how much. But remember, this is going to be in conjunction with, how many times was the file accessed on every program invocation, right? So you're combining these tweaks in some way. Now, well-known log directories and temporary directories might need to have their rank decreased, right? Again, not a truism, but an observation that something like user bin last, which is supposed to tell you the last people that were on the system, if it can't find wtemp, it doesn't actually crash or break or whatever. It just tells you that nobody was been on the system in the last whatever period of time. So does it depend on wtemp? Again, it's a very fine line. If you say it depends means that it needs that to function correctly and it's not going to crash or cause other programs to crash, then no, it doesn't depend on it, right? But if it does cause some kind of behavior that's really egregious, then we will say that there is a pretty strong dependency there. And then there's files like, there's programs like Emacs and lots of other programs, even Oracle, that write and read to files in short intervals, right? And again, we're sort of searching, we're grasping for this idea that these files are not essential to the functioning of the program. They may be essential to the behavior, in which case we want to take another look, right? But if Emacs finds that this file, which has a hash mark in front of it to represent a temporary file that it keeps in memory as you're editing it, and then it writes to the permanent file on the disk, if Emacs doesn't see this file, even in its running, we know that Emacs is not going to crash. It may be very bad for you because you're working on something, and if you erase the buffer, for example, you're out of luck. But you can imagine lots of other programs that are writing intermediate results, for example, to the disk. And those are necessary to the functioning of the program, right? It's not just libraries. It's if it tries to read this now non-existent file, or if it tries to read corrupted data from the file, it may very well crash. Okay, so now we get to the gentleman's question a little bit about popular objects in the graph. So a colleague of mine at Harvard worked on something called ProvRank, which sort of copies the idea of PageRank, except with provenance. And what he was studying was, if you have an underspecified query, a query that could essentially resolve to, show me the entire graph above this point, how do you stop it? How do you curtail the request to only those things that are interesting? And it's a difficult question. One of the things that he came up with was taking the presence of an object across all lineage queries. So if you observe that something is constantly in every query that you have, right, it's not really that interesting. And so I extend this idea that these popular objects are less likely to be the singular cause, for example, of one or two symptoms that you're seeing. And the most egregious case I can give is if libc is corrupt or missing or whatever, you're going to know right away, right? Because everything depends on it, practically. So we may end up reducing the rank of the edges or the paths or the subgraphs that include those popular objects. Not down to 0, but certainly not at a very high confidence, because if it includes that, it may be that you know, there may be more evidence that it should be in some other part of the graph. Yeah.
Also, a follow-up question on this is it easy to like extend your system to have some kind of delta debugging feature in it, based on the intuition that okay, now I know, for example, that the DNS example just raised failed, right? And I know it was working, let's say, 1 day ago, and I had whatever the snapshot of your system 1 day ago. I know that was a normal snapshot, and then I just look at today's causal relationship, this chain, and do some delta based on that. So you can isolate, okay, what is the delta?
So there's two aspects to an answer to that. One is that, you know, this system doesn't have to be used in exclusion, right? It can be used with other well-known techniques for finding, you know, something doesn't work today and it worked yesterday. What changed, right? It's a very simple view. But then when you're looking at the things that have changed, you know, you may get this really big set. Right? And without more domain knowledge, let's say you're a junior sysadmin and you don't know this complicated application, then maybe you go into the provenance graph and you're able to issue queries that will ferret out, you know, give me things that have changed within this day but that are along these paths back from the symptoms I'm seeing. Right? So in a sense, you can do some of that in here, and some of it you may want to supplement with other traditional techniques like tripwire, for example, about what's actually been modified on your system. So, and then lastly, you know, I perceive that we would want to have these what-if scenarios that sort of allow the domain knowledge to come in even more. So what we're talking about is that if somebody sees something that has been ranked semi-automatically by the algorithm that doesn't really look right, doesn't seem right, that they can maybe tweak it and kind of see what other query results obtain. Well, I'm going to talk about that next, actually. Yeah, I'm running a little bit late. So now we want to be able to assign. Now that we can assign edge ranks, we want to maybe compute ranks for other combinations of nodes, right? So we're going into this huge graph, and we want to be able to basically trim the graph and find nodes of real interest to us. Again, another naive ranking. You know, take the arithmetic average of the edges on a path if you're trying to rank that path. Okay, so this is an example of, again, wire test, fixed mount. These are a couple of binaries that are linked when you compile the AMUtils. And so this path right here, you know, these were maybe, say, the base ranks that we established, or maybe the tweaked ranks. And we want to just assess the rank of this path. So we can say that we'll just take the average, and it comes out to 0.75. Okay, well, you have libc 24 SO here. This libc was not used to actually link to wire test, right? It was used by GCC. GCC used it as its C library, right? But this libc is ostensibly the one that wire test will rely on, right? So the question is, and obviously the libc that we actually use to link in with wire test is not in this graph right now. It's been elided, but you know, if we rank this path and then we rank this path, well, both of these are ultimately inputs to wire test, right? Both of these. This is a much farther away input to wire test in some sense, right? And there may be absolutely no dependency on libc 24, right? But our queries are going to find that in some combination, right? So this shows some of the disadvantages of being able to rank with just, for example, an arithmetic average. We want to take into account distance, right? Distance effects, maybe a weighted average. How far away is this actual thing? Does it make any sense to even talk about if it's gone through GCC and we know that it's loaded by GCC because GCC needs it, then wire test doesn't need libc 2.4, but wire test needs libc 2.6, right? Now, this may not actually happen in practice, but I just wanted to show you sort of some of the complications of finding out not only where to stop, but how to discern the difference between two pieces of provenance that may be ranked similarly. Right? I didn't rank libc 2.6.so because it's a direct dependency. It's going to have a rank of pretty much 1, right? But I may have a situation where I have libc 2.4 and I have to consider it as a problem. Libc might not be the best example either because, as I mentioned, libc is pretty relied upon by a lot of objects, so it might not even enter into the rank. So if you start to extend these techniques to rank entire subgraphs of interest, you can start to come across ranks and patterns that you will see for particular applications and for particular programs. And all of this needs to be able to be queried, right? So we have this SQL-like language called Pickle that we developed, and it allows us to extract information programmatically. So we have, for example, the query, for every process whose executable is or was sendmail, retrieve its direct dependence from the last 24 hours. Dependance, right? So we select P and F from the entire provenance graph, which is probably not a good idea. We want to trim this down first. And we bind that to P, and then we have the executable is X, bound to X. The input at time E is bound to F, and then we have these characteristics. Now minus E time is less than a day, right? So we're going to get back a set, essentially. We can get back a set. We can ask for a set of the edges. We can ask for the set of the nodes, or both, right? And now we've ostensibly trimmed down to something that might be of interest to us. Another example is retrieve the name of every direct or indirect process ancestor of httpd.conf that also has a direct file ancestor that was owned by me. So in this case, we're going to, this plus here, for example, means that we're going to go back through the graph and look at every single process ancestor that contributed to C, this whatever node we find. And then we have these restrictions on the actual path. So this can be really, really powerful, but again, it needs to be tempered in some way. And you need to be able to know that you're getting queries that make some kind of sense and that are just not going to lead you on a wild goose chase all the time. And that's where the ranking would hopefully come in. This language doesn't have ranking in it yet, or some similar measure that we will have. But you could easily imagine being able to put ranking in there and say, I don't really care about results that have anything less than a 0.5 ranking or something like that, or less than whatever, some arbitrary ranking. And as a system administrator, you'll have to definitely experiment, right? Especially at your site, and from the knowledge that you have. Now, system administrators are not very likely to be wanting to write queries all the time to troubleshoot problems. This is supposed to make things easier, right? Not harder. So we imagine that we're going to end up actually building sort of tools to either visualize or visually construct queries, or tools to develop a storehouse. So basically, query suggestions. Like this was actually looked at by a system administrator, and these are the kinds of queries that worked for these kinds of symptoms. And maybe we put those in a storehouse. We integrate them in a storehouse with a trouble ticket system. So if you see symptoms that are similar, maybe start with these kinds of queries, these basic building block queries, right? And then refine and refine until you get to it. But a lot of these queries will be canned, right? They'll be sort of very easy to just plug in and use and give you back a list of things with the top 5 likely candidates. If you end up exploring all of those and find that it's not good, then maybe you need to go back and tweak the ranks or develop other queries as you're going along that will be recorded and that can be later explored again. So that's part of the query storehouse that I'm mentioning. We want to maybe be able to explore useful provenance patterns. So maybe there's Apache sort of always accesses at your site roughly the same types of things. So we want to be able to sort of put a bubble around that subgraph and say that things that are outside of this bubble are much, much less likely to affect it because it never goes out to these trees or to these parts of the file system or the network, for example. And we may be able to use things like graph isomorphism, right, to compare typical runs of programs and what their provenance looks like. And you can also imagine that this is not just a good utility for troubleshooting, but also for exploring, for example, malware. Right? One of my goals, one of my newer projects is hopefully once I get this prototype done, is to set up something like a honeypot, right, where I allow attackers to come in and put on whatever malware they want, and then I analyze the actual provenance graphs and what do they look like, right, and what kinds of conclusions can be drawn from where the geography, where are they coming from in the world, and the construction of them. So this is sort of like a black box perspective, right, for malware, if you will. And then I talked about making the provenance collection platform agnostic. So right now it's fairly fragile because we actually modify the kernel's VFS layer and several other things. And we hook into the task struct and we hook into the D entries and we add information to the inodes that there's provenance hanging off of these files. And it's in what we call a stackable file system. So the stackable file system is like at the basis for eCryptFS, if you've ever seen in the Linux kernel, in the Linux distribution. And the idea is basically that you send requests down through the VFS, and the first layer it hits is our layer that collects all the provenance, and then it sends further requests as if this layer wasn't even there down to the X3 or whatever the underlying file system is. Every time the kernel changes, several of these objects, several of these structures are changed. Not every time the kernel changes, but frequently. So my idea is that basically, if we can move it into the hypervisor in some way, it'll be a little less fragile because hypervisors don't change as frequently. And the actual task structs, for example, we won't be looking at the file system anymore necessarily. We'll just be looking at the structures that contain file system information and task structs and things like that. And the fundamental changes don't occur to those as frequently as they do to things like the VFS. So it might be more likely to be adopted, right, into like the hypervisor kernel stream as opposed to upstream in the Linux kernel, sort of as a third-party modification. It's not unheard of, but it's much harder. And the other thing is that we can collect information from really from early boot, which we can't do exactly right now with the file system that we have, because certain things need to be loaded prior to this stackable file system to actually be put on top of the underlying file system. And so that's a non-starter for system troubleshooting, because practically all of your root daemons and everything run from the root volume, so you lose sort of a lot of this boot information and things about when processes are just starting up at the beginning. But in the Zen form of this, or the hypervisor form, we can trap all of these system calls, reach into the guest memory, pull out the important information, and send it to, for example, a daemon that's running in the control domain, like DOM0. And the last thing I just want to mention is that there's a lot of different aspects and faces to system administration, and the ultimate goal is to really just answer the needs, either business or otherwise, of the organization. So we may want to be able to use Provenance for change impact analysis. Again, giving you what-if scenarios where you say, well, if I change, if I move this configuration file there, or if I free up disk space over here, how is that going to impact these programs? And I might have a better idea of how it will because I know the connections. And so here we have our trusty little system administrator thinking all these fine thoughts. And that's my presentation.
Okay, so in the troubleshooting, you're talking about mainly about configuration problems.
Am I talking about?
I mean, the troubleshooting you talk about is it mainly about the?
Well, it is the case in a lot of areas that configuration and manual configuration is one of the largest causes of problems. When humans get involved. And things aren't as automated as they could be. A lot of the time, now automation has its own pitfalls, right? The scripts that we write these days, and even some of the more sophisticated configuration management utilities are kind of fragile, right? Especially scripts. I mean, scripts, they defy all logic sometimes. And unless you have a really, really good understanding of everything that your script is supposed to do and interact with, you can get into some tough situations where you don't even know if it was that script, for example, that caused the problem, right? With the Provenance, hopefully you'll be able to look back and say, okay, well, this has some kind of a direct connection or an indirect connection to this. Are we going to find that, hundreds of scripts link back to an individual problem? We may, but it's probably a lot less likely, because once something breaks or once something is sort of in the process of breaking, right, other scripts that are not generally very robust will encounter a situation that they're not designed to handle, and they will break themselves, right? So actually, you may get more evidence that some progenitor script is broken, or got the wrong input or something like that. So we're not just talking about system configuration, but it's certainly one of the areas that administrators will want to use the most to track down problems, because knowing that there's a very high probability of it having been a configuration problem. And you can, obviously you can combine this, like I said before, with other techniques, model checking, if you have an idea of how it's supposed to be configured, things like that. And you don't have to just leave it to this. In fact, no system administrator worth their salt will ever just rely on one approach, right? So, does that answer your question?
Because the reason I ask is it seems that most of the nodes in the dependency graph is about files, right? So does that assume the problem comes from a particular file?
Well, it doesn't have to, right? I'm working on lots of vectors of input. So I'm developing now a model of network provenance. What does it really mean if every one of your systems at your site is instrumented in this way, and you can communicate and collect provenance from all of them, and they're all under your domain, easy peasy. You can make correlations between the provenance, and you can look at which ones are communicating with each other. But when you start to go out to an open world, and you say, okay, well, my server is communicating with 100 clients, or my server is communicating with the cloud where my database server resides. then it gets a lot more difficult, right, if you don't have control over it. And so what does it mean to have network provenance? What does it mean to have something coming in? What can we nail down? What can we tell about the provenance? Does it help us in any way? A lot of the time, and then you've got encrypted connections. It's like, what kind of information am I going to get with that? I can potentially get some provenance out of net flow analysis and things like that, right? We're talking about a really comprehensive ensemble of tools and methods to really get to the cause of problems. And I know there's been a lot of work on, debugging distributed systems in various ways, Magpie and those kinds of systems. And I don't exclude this from anything. I just look at this as more of another source of information. I've just tried to narrow it down to a specific task that you can do on one or more locally controlled systems.
Sorry. I have a question. So basically, I see that the granularity of your troubleshooting is, as he said, is files, right? So basically, if, for example, I find that my Apache doesn't work, then you tell me that, okay, this is because httpd.conf has some problem. But it doesn't help too much, right? Because I don't know what exactly the problem in this big configuration file. So I just wonder whether it's possible that the Provenance technique can dive into this kind of big bunch of configuration files and tell me what is the dependency between these kind of code or configuration file entries, and then you can give some better.
Well, while that might be doable on sort of an application by application basis, in a general case, right, you don't want to. You want to be able to add semantic content as you go along and ideas of how things are supposed to work, but on-access sort of parsing of things that you don't necessarily understand the content of, right, would be very difficult to figure out. I mean, maybe you can give some kind of a schema that says, if the file is, has these sections in it, then there's sort of a sanity check and things like that. But Apache and a lot of applications already do that kind of thing. So again, you may need to combine this with other things. The main thing is that, if you find out that it's httpd.conf, okay, as a system administrator, you have to usually live with the fact that HTTPD is a very complicated program. SendMail is a very complicated program. And debugging that inside itself, this really isn't designed for, right? Because again, you need knowledge about what those configurations mean for Apache or for the behavior. So we're really just guessing, and we're guessing to give us a leg up in terms of finding the more complicated ones that stretch back to through different kinds of configuration files and processes that might have generated that. And there are a lot of those, especially inter-process communication now with the dbus and things like that. May not be used as much on server systems, but is definitely still there in some way.
I think the resolver example used is very suitable for this situation. But do you have a sense of how many cases are like this complicated? Because it has to track one file and some other process modify this file, and then it is affected by another file. I'm not sure how many cases are like complicated like this. For example, if it's like Apache or MySQL, most of the time you just track the http.conf and you end up with the second node. It's just like reading or Emacs, and it misstops that.
Yeah, I mean, it stops, wherever you're doing manual manipulation of configuration files. It definitely stops with a human being, right? To a certain extent. But you could imagine maybe even some additional information, like correlated around the time that I modified this configuration file. I looked at the man page for something, right? And maybe I looked at, this man page. As the computer can't know what I was looking at, but the fact that I looked at a man page maybe can give me some clue as to what I was, sort of part of my thought process. And so we're thinking about like, this is in the moment, but really think about it like I made this change 6 months ago, and there's some kind of a weird interaction with something new that I put on the system that it doesn't show up until now, 6 months later. Well, what was I thinking back then when I made those changes? This kind of institutional memory, it's really hard to collect in a generalized way, right? A lot of the time in trouble ticket systems, for example, you want administrators to enter as much information as possible about sort of not just what they did, but also the thought process that led them to not just troubleshooting, but doing whatever the task is. And I don't see an easy way to solve that. But giving them more knowledge and more sort of a little bit more transparency into the potential connections between components in the system, I think will help them. How much remains to be determined. Yeah.
Firstly, very wonderful work, very intriguing. I'm wondering, do you have implemented this idea, and do you have any evaluation results? For example.
So so far we have the original systems were called Provenance aware storage systems, and like I mentioned with the BFS layer. And what they did was they did a bunch of examples where, for example, you have to find, where in this workflow this image got corrupted or something. You're looking at medical data, medical images or something, and so they've done these sort of, I don't want to say they're toy problems, but they're not widely applicable, right? To look at this kind of thing, and they've assessed the performance of the current Linux kernel implementation at anywhere from 3% overhead to 21% overhead, depending on how much I/O you're doing. There's ways to tackle that, but I haven't been able yet to collect this direct information that I'm speculating about because I'm still finishing up the prototype. And I imagine actually by the end of this semester, you guys don't use semesters, right? You use quarters, right? So by the end of next quarter, I'll probably be done with that. And so I'm really looking forward to seeing what it looks like. It took a while to get here because hacking the kernel and hacking the hypervisors and stuff are pretty, it's touch and go, especially because I'm not a super kernel hacker.
Well, I think it's very hard to get the ranking right. For experience, like system administrator, they know for a particular kind of a symptom, they know where to look at. The first file to look at, the second configuration to look at. But your system, you kind of just aggregate all the information, and you have using your ranking algorithm to suggest those new system administrator which file to look at first. But how can you make the ranking right? So as you said, you will increase or decrease some of the priority or the probability of some dependencies, but how specifically, how many will you increase or decrease?
Well, so there's two things here. Remember that it won't exist in a vacuum. So, my assumption is that if senior administrators, start to take a look at the system, they will be able to essentially input into the system guidelines for ranks that will make much more sense to them in their site, right? So when a junior administrator walks in, he's not just relying on this system. He's also going to be, using obviously his own skills. The other thing is, I'm looking also at, taking the edges and turning those ranks or probabilities, if you will, into a Bayes net, right? Which would be more robust to incorrect probabilities or slightly wrong probabilities, for example. And seeing where we can get with that kind of approach about the likelihood that something is descendant from this one file or these 2 files or 5 files or whatever. Yeah. Oh. Oh, okay. Thank you.